Hey guys, it's AJ from Design the Everything. Today we're going to talk about fits, tolerances, and allowances on 3D printed parts. Now, whenever you make something that has two mating surfaces, if you make both of those surfaces exactly the same size, it will not fit together. If you have a 1-inch hole and a 1-inch peg, they will never fit inside each other. Now, in CAD, yeah, that might work. A 1-inch hole will fit in a 1-inch peg because nothing's actually manufactured. When it's digital, when it's inside the CAD program, everything is exact. The walls are perfectly smooth. The hole is actually 1 inch. The shaft is actually 1 inch. There's no imperfections left from the machining process. When you design two parts that actually go together, you apply what's called a fit. The fit describes how closely the two parts fit together. There's a couple of different kinds of fits. One is called an interference fit. Now, interference fits are the ones that are the hardest to put together. That means your shaft is bigger than your hole. And so to get the shaft in the hole, it actually takes a lot of force. These are used a lot of times with bearings on a shaft, where the bearing will be just a little bit undersized, and to get that bearing on there, you actually have to heat it up so that it expands and it'll fit on the shaft. One step down from the interference fit is called a locational clearance fit. Locational just means that when you put the shaft in the hole, the shaft is not going to move around any. And clearance means that the hole is bigger than the shaft, at least just a little bit. So this could also be called a press fit. It will take a little bit of force to get the shaft in the hole, but not a ton. The loosest kind of fit is called a running or a sliding fit, which is exactly what it sounds like. The shaft is small enough that it slides easily inside the hole. Running sliding fits are the most common type of fit. They're used everywhere. Now, when you're calculating these fits, there's a couple of different things you want to take into account. The first thing you need to take into account is your tolerance. Tolerance is determined by how accurate your parts are made. So if they're machined, it's how accurately they're machined, or if it's 3D printed, it's about how consistent those 3D printed parts are. A tolerance doesn't have anything to do with your designed value, but rather it's how different the real value might be from your designed value. So if you have a part that's 1 inch and you're finding out that half of your parts are 1.1 inches and half of your parts are 0.9 inches, that means you have a plus or minus 0.1 inch tolerance. When you are first designing your part, in this case it was that 1 inch number, that is called your nominal dimension. So if you made 100 parts and measured them all and plotted them, you should get a bell curve with your nominal dimension right in the middle. So in this case, it's 1 inch. And then half of the parts you measure will be greater than 1 inch, and half of the parts you measure will be less than 1 inch. And if your process is in control, one standard deviation in either direction is your tolerance. So minus 0.1 and plus 0.1 from that 1 inch is one standard deviation away. When you're sending a drawing off to a machine shop, you can specify the tolerance. You can specify it as 5/1000ths of an inch or 1/1000th of an inch. If you wanted to, you could specify it as 100,000th of an inch. But that machine shop is going to charge you a lot of money for that precision if they're able to do it at all. If you're able to raise that precision, if you can design a part where you can tolerate 20,000ths of an inch tolerance, then that'll save you money because that machine shop is going to be able to put a little bit less time into each part, and they will have to throw away less in quality control. Now, when you're designing two parts that fit together, there's a couple factors that come into play. I already talked about tolerance, but there's also one called allowance and another one called clearance. Allowance is the smallest gap that you could have between the two parts. So if you have your hole and you have your shaft, and you take the biggest shaft you could have and the smallest hole you could have, and you find that distance there, that's called the allowance. If your allowance is too small, there might not be enough room for the shaft to go into the hole. Or if there's too much allowance, it means your fit will never be that precise. And if you have a fit that really matters, like a piston in an engine, if your allowance is too big, you'll never get the tight seal or the positioning, or you'll get too much vibration or gas escape. Clearance is the widest difference you could have between two different parts given their tolerances. That means you have a hole at its biggest and the shaft at its biggest. You can use the clearance to figure out the maximum amount of wobble or play that your parts might have. Now, when I'm calculating fits for a machined part, I use this guy, the Machinery's Handbook. And inside it, it has all kinds of charts. You don't have to have this nice $100 book. You can find them on the internet. Just do a search for a fits chart, and you'll find lots of them out there. Just make sure that when you find a chart that you pay close attention to the units that are being used on the chart. All the ones in Machinery's Handbook are in thousandths. It'll say something like hole plus 1, shaft minus 0.5, but that would actually mean that would be the hole plus 0.001 and the shaft minus 0.0005. Now that's great when you're sending something off to a machine shop, but that does not help you with 3D printing. When you're 3D printing something, you do not get to set your tolerances because it's all based off of the capabilities of your machine, which are way less precise than something like a Haas CNC machine that can hold thousandths or 10,000ths of an inch. So today I'm going to print a bunch of test parts at a bunch of different sizes and see if we can really dial in what the tolerances are on my printer and what the difference in sizes between the shaft and the hole need to be for all of the different fits. So I'm going to go ahead and print out a test piece. I'm going to do probably 3 or 4 different sizes of shafts and a bunch of different sizes of holes so that we can see which ones go together, how they fit, how loose they are, how tight they are. So this is my model. I've got my 3 shafts and a whole bunch of holes. If we go into the sketch here, you'll see the sizes on them. So I have 3 different shafts and 3 different sets of holes. The shafts are, well, they double each time going up, so 0.25, 0.5, and then 1 inch. And the holes, they go up by 5 thou each hole, except for the 1 inch holes. 1 inch holes just go up by 10 thousandths or 100th of an inch each one to save some space. Total thickness here is 1/4 inch. The shafts are 1 inch. So I have my test pieces off the printer. I actually ended up printing 2 of them. One at standard quality and one at low quality. So if you look at this here, I have the peg in the first hole that it'll run smoothly in. So I can easily move that back and forth, move all of these. Now this is the high quality one. So on the 1/4 inch peg, it moves smoothly in the 0.255 hole. So 5 thousandths of an inch for it to move smoothly. Which is actually way better than I thought it would be. Exactly the same thing in the 1/2 inch hole. It only took that extra 5 thousandths to make it fit smoothly. Actually, I noticed on both of these, they will fit in to their first hole. So you actually can put a 1/4 inch peg in a 1/4 inch hole with this print. Though I think that has a lot to do with the fact that the plastic actually shrinks as it cools. So I think the peg and the hole are just a little bit undersized coming off of my printer. The 1 inch peg fits smoothly in the one that's 10 thousandths bigger. So that hole would be 1.01, so 100th of an inch bigger to slide smooth. Now the lower quality is much different. So the 1/4 inch peg starts to move smoothly in the one that is 35 thousandths or 0.035 inches bigger than the 1/4 inch. The 1/2 inch peg, it takes 8 holes, so that would be 40 thousandths different. Now with the 1 inch peg, remember the holes are 1/100th of an inch apart instead of 1/2 of a 100th or 5 thousandths. It took 4 holes, so this one also takes 4/100ths of an inch to move smoothly. Now on all of these, if you go back 1 hole, you get a fairly tight fit. And if you go back 2 holes, it's still possible to force them in, but not necessarily easy. So in short, if you want a smooth sliding fit on normal quality settings, you want to leave about 5/1000ths of an inch gap. If you are on rough quality settings or your printer just can't keep the same tolerances as a higher end one, then you want something like 30 or 40/1000ths of an inch. Remember, with all those measurements, you can tweak them a little bit up or a little bit down to find exactly the type of fit that you want. I just made an account for Design the Everything on Thingiverse. You can find it by just searching for Design the Everything. Click on the link in the description below. Right now, the only thing I have on it is this, but I will be uploading the rest of my projects in the future as I go. And if you'd like me to upload any of the past projects I've done, just go ahead and leave a comment below and I'll get them up there. Thank you for watching. I hope this was useful for you. If you liked what you saw, please hit the like button. If you want to see the rest of my videos as they come out, please subscribe. If you have any questions, leave them down in the comment section below, and thank you for watching.